In chapter 1, we're gonna learn about the building blocks in proteins. Proteins, they are made up of amino acid by peptide bonds. Proteins, they do have four different levels of structures. Primary structure, indicating residue sequences. Secondary structure represent local regular structures present in protein world, like alpha helix shown here. Tertiary structure indicate three-dimensional structures of single polypeptide. Quaternary structure indicate 3D structure of protein with more than 2 polypeptides. We are looking at common structures of 21 standard amino acid. Of course, there are more than 21 amino acids in life, but the standard amino acid defined as amino acid being used in translation on ribosome are very limited. Some books they just tell 20, some 21, but should be more than 21 actually. Selenocysteine has selenium in the position of sulfur of cysteine. This amino acid share three things: alpha carboxyl group, alpha amino group, and lastly hydrogen atom. This might be different in side chain. We could locate atom positions commonly used in the organic compounds, starting with the Arabic number 1, 2, 3, 4, something like that, starting with some the interesting group, in this case carboxyl group. The Greek letter system just starts right after interesting group, in this case this position: alpha, beta, gamma, delta, epsilon, something like that. There are several types of side chains R group in standard amino acid. This slide shows you non-polar aliphatic side chains: glycine, alanine, proline, valine, leucine, isoleucine, methionine. Glycine may not belonging to this category. It could be controversial because this hydrogen atom is smallest one, so that it could be different from the rest of parts. But in this slide, they just include it in this category. Second group will be polar uncharged group. Serine, threonine, cysteine, asparagine, glutamine. Third group will be aromatic group. phenylalanine, tyrosine, tryptophan. Next group will be negatively charged group, aspartate, glutamate. Next one will be positively charged group, lysine, arginine, histidine. Each individual amino acid has a full name, as I mentioned. In addition, 3-letter name. For glycine, it's just gly. Alanine, just ala. Just using first three alphabets of full name. But certainly, there are exceptions to this rule. Isoleucine, tryptophan, glutamine, asparagine belong to exceptions. Just remember 4 cases. Other rest of things will be following first 3 alphabets. Nowadays, 1-letter name is popular. So use in this case first alphabet of flame, GA for glycine and lysine and alanine. Again, there are exceptions to this rule. F, W, Q, Y, N, D, E, K, and R. So only remember exceptions that could help you. Some cases, D, or for the 3-letter name, A, S, X represent 2 types of amino acids, D and N. Again, G or GLX stand for 2 types, E and Q. I'm going to explain some properties of amino acids. First, stereoisomer. As you see here, amino acid, alanine in this case, could present as L or T. All amino acid utilized in translation are L type. Okay. Isoleucine and threonine, these 2 amino acid has 2 asymmetric carbons. The other one is in side chains, this position, and also this position, so that they could form different isomers may be possible. Amino acid could function as both acid and base. Okay, so as you see here, this could be converted into this form, meaning playing as base, acid, releasing proton. Instead, it could accept proton functioning as base. Such property is called ampholyte or amphoteric electrolyte, meaning having both acid and base in one molecule. Itself, if you look at this amino acid shown again here, two groups, they charge it differently. One negatively charged carboxyl group and positively charged amino group at neutral pHs. Such feature is called Jupiter ion or dipolar ion, meaning hybrid ion and neutral pH, plus minus different charges together in single molecule. As you know, amino acid could have three different ion forms depending on the pH and pK values in general. At extremely low pHs, it could exist as a positively charged amino group. So altogether, plus one charge, less charge. As pH increases, the proton in carboxyl group could be released, making this kind of Chapt ion. So net zero will be 0. Further increasing pHs could make this kind of another release of proton from amino group. So net charge will be -1. So this titration curve could be obtained by adding alkali to amino acid. So indicating two pK values corresponding carboxyl group, and secondly amino group, respectively. So the average value of two pK values is considered PI, isoelectric point, where net charge will be 0 for this amino acid. This slide just summarizes the type of group. Aliphatic again. Proline will be actually exactly called cyclic imine group, not the amino group, because side chain is just connected to the amino group. Aromatic sulfur amino acid, hydroxyl group containing amino acid, serine, threonine, and amide containing amino acid, asparagine and glutamine, basic, and this is wrong, amino, the acidic carboxylic amino acid.